และลำดับถัดไปนะคะก็ถือว่าเป็น Special Lecture Special Talk มากๆเลยนะคะขออนุญาตแนะนำประวัติของผู้บรรยายในวันนี้ก่อนนะคะสำหรับผู้บรรยายในวันนี้นะคะคือท่าน Mr. Jun Paik Co-founder and CEO ของ FuriosaAI นะคะเป็น Master of Science in Electrical and Computer Engineering from Georgia Institute of Technology former hardware engineer AMD and Samsungมิสเตอร์จูนไพค์เป็นผู้ที่มีชื่อเสียงในแวดวงอุตสาหกรรมเซมิคอนดักเตอร์สมัยใหม่เป็นผู้ที่ออกแบบพัฒนาชิปเร่งความเร็วในการประมวลผล AI แบบ LLM NPU และ Computer Vision RNGD and Warboy ที่มีประสิทธิภาพทางพลังงานมากที่สุดในโลกFuriosa ก่อตั้งโดยอดีตวิศวกรของ AMD Samsung และ Qualcomm ปัจจุบันบริษัทมีพนักงานมากกว่า 100 คนรวมถึงเป็นผู้นำแล้วก็เป็นที่ปรึกษาที่มีประสบการณ์หลาย10 ปีที่ Meta AI Western Digital Sun Microsystem Grok และ Intel ค่ะและในวันนี้นะคะมิสเตอร์จุนไพค์จะมาบรรยายในหัวข้อความท้าทายการออกแบบคุณสมบัติและประสิทธิภาพของชิป AI Accelerator กรณีศึกษาการใช้งานจริงแผนงานและอนาคตของชิป Now I would like to invite Mr. Jun Paik to give a special talk today and please give him a big hand
Thank you very much for inviting me to the institute here, King Mongkut Institute of Technology. It's the first time for me to visit this city and Thailand, so it's so good to have this chance to introduce us. So I'd like to today talk about more. Today I saw the presentation on more AI application and AI algorithm, but I'd like to talk more about this computing side, especially the computing means it's a kind of a semiconductor technology. So I think there are a lot of electrical engineering students and computer science students. So I'd like to kind of share kind of our perspective, how we view this AI computing space, how we develop our semiconductor product, and also introduce our product, and potentially how we can collaborate together on this kind of important agenda. So screen looks like quite dark, but let me show you our chip product first, so you get some sense, feeling about our product. So this is our second generation product that we call like Renegade. A lot of our product name comes from the movie Furiosa. Our company name actually comes from the movie. You see the release of movie Furiosa actually. So. Actually, the movie Furiosa actually was released about 9 years ago. Actually, it was when our company got started, actually. I just saw the movie, and I have 2 more co-founders, and I just say, okay, we just name our company Furiosa. It was quite a temporary name, but it turns out like we just settled down with that name now. And we had our first generation product we call like Warboy. I didn't bring it today, but we are now about to launch our second gen product called like this Renegade. If you see this chip, it's quite a big chip actually. It's quite a large chip. It contains almost 40 billion transistors inside. It's fabricated on TSMC 5 nanometer node, so it's quite advanced node. And if you see here, there are 2 rectangles here, if you can see. They are actually the HBM memory. So if you have heard of HBM, HBM is a very high bandwidth memory to provide a good sufficient amount of bandwidth to this computing SoC. And actually, you don't see it, but like between this SoC chip and HBM, there is another silicon beneath, we call like a silicon interposer that connects this SoC with this HBM. So it's we call like a 2.5D packaging these days. So we enabled this product in partnership with TSMC and memory vendor in Korea, which is SK Hynix. And I mentioned also another thing is this contains almost 40 billion transistors. If you think about the amount of transistor inside, you know, the total population of the Earth right now is roughly, I think, 6-7 billion, right, people. But it has like 5 times more people in this small, like a rectangle. They are all interconnected together, right? So you can imagine the scale of this design and the complexity. On top of this kind of like a frontier memory technology, putting into this product. So why we are developing this kind of a product? What's the purpose? Why we are doing all this endeavor, actually? The reason is because of AI, actually. It's all about AI. Why we are pushing this kind of semiconductor technology, and the faculty in the previous talk talked about this chatbot dialogue based on the LLM models. But if you think about the naming of LLM, it's actually a large language model, right? Large language model, meaning that it's a big, huge neural networks, right? We are very, I guess you guys are very familiar right now, the size of this neural network model these days, we are talking about a trillion parameter scale, right? So this neural network, if you count all this weight connection, it's almost like a trillion kind of scale. The ChatGPT 3 was 175 billion parameters. But now we think the most state-of-the-art model, the most capable AI model we are talking about, provided by such as OpenAI, Microsoft, is almost like a trillion scale. Of course, there are many efforts to downsize those models into so-called like a small language model, so that it's more specialized and it can run more specialized tasks more efficiently, so that it can run on like a PC or on your mobile phone. But still, many powerful AI models still are very big models, still like running in the cloud, actually. It cannot run on your device because the model is so big. It's why you need this kind of high performance chips dedicated for AI. We put 40 billion transistor and all this HBM technology because we like to run those large language models as efficiently as possible and also as high performance as possible. So that's kind of brief introduction of what we are doing, what we have been doing so far for the last 7 years, starting as a startup company. We are now around 150 people team. It's still a small team, but still trying to build a quite complex system, like all together. So let's get to the next slide. Yes. So I like to quote a certain these days quotations from people. It's like mentioning that compute is going to be the new currency of the future, because the role of a compute, especially in AI age, is quite I'll say, different. I mean, getting more kind of significant. Actually, computer itself always played very important role in powering the PC, smartphone, and everything we do. But the role of computing is going to as ever important at the moment because AI, as I mentioned, is basically kind of big neural networks, and it requires unprecedented amount of computing, and the way it's computing is quite different from the previous way of the software, like applications are consuming computing actually. So, so the Sam Altman, like as you know, like OpenAI, I think it's like compute is kind of new, very expensive, valuable commodity in the future. You can obviously see, if you see all the crazy stock price of NVIDIA and all these kind of new AI computing space company, I mean, you can see that it's quite right now, this computing is going to be more and more important in this entire AI ecosystem and the value chain. So let's look at what's the cost of this compute. That kind of look at the scale of a compute we need. Let's say we like to run such as GPT-3. So GPT-3, the architecture, model architecture of GPT-3 is pretty much open. So I think the students here also probably studied, I think, the transformer architecture. GPT-3 is decoder-only transformer architecture. And it's basically kind of 100 stacks, many of the same block of the transformer block stacked together, stacked kind of almost like 100 stories. And if you look inside that transformer, one of the transformer block, there is a so-called like a feed-forward network. I'm just here, this matrix computation here is just one feed-forward network, what kind of computing we need there. You see here, like this is, we can express all these neural networks as a more kind of tensor, matrix kind of multiplication. Actually, the truth is like you are talking about more generalized kind of a matrix. We call we call more in general term like a tensor kind of computing. You see about here, the dimension of this matrix is that on this row side, it's almost like 10,000, right? So we cannot like put everything here. I mean, in just small slide, but this row is actually 10,000 kind of elements. And this column is almost like 50,000, actually. So you are talking about the computing 10,000 and 50,000 metrics are kind of multiplied together in just one decoder stack, right? And I told like the entire decoder transformer block will require 100 times repeating of this almost the same block. So this computing will be repeated almost like 100 times. This entire thing also have another matrix computing as well, but just this computing will, this part of matrix computing will repeat it like 100 times. If you repeat 100 times, then what's happening is you are just generating token here, right? But for ChatGPT, it's not just one token, right? So your output length sometimes can be like 100 or 1,000. So you are generating like, let's say, 1,000 tokens here, meaning that this computing repeats 100 times, again repeating like 1,000 times, right? So if you do that calculation, then they just answer one of your query. So how much computing it is. It's, even though it looks kind of simple, when we just enter prompt, we get the response, but between that query and output, there is so much computing happening. Meaning that we need a really, really efficient computing to sustain this kind of AI services to more and more people. If we don't do it, then it will consume all the energy available here in the Earth, even. People are really talking about it. Already, the AI computing itself is spending the energy at the scale of the nation. But if you use more and more of AI, it will use more and more energy, meaning that to make AI computing more sustainable, we should make this computing, each part of this computing, much more efficient and sustainable. It's the purpose we are developing this kind of a chip that can replace the current paradigm of computing, such as a GPU, which we think is a kind of inefficient paradigm. One good analogy that I have is that it's a very advanced gasoline car, but we need to move to electric car because electric car is the future, the more sustainable kind of way of transportation. The same thing here. The AI computing also needs to be much more sustainable, meaning that we need a kind of newer engine that are optimized for AI in a native way. So it's why we are pursuing this kind of development of a new kind of AI chips. But what's the challenge here? I mean, I like to talk about the technical challenges of developing AI chip. So I just mentioned about the importance of AI chip, but what's the challenge of developing AI chips? Because like we started about 7 years ago, but there were around 100 companies over the world who developed the same kind of AI chips at that time, startups and big companies. Like I will say, there are like 100 different efforts to develop this kind of AI chip, but none of them actually got successful so far. You see still even more dominance of a GPU approach than this new AI. So it turns out there are many challenges developing this AI chip. So one is that this AI models are changing so fast, right? So you are developing this kind of a new semiconductor product that are optimized for AI computing, but your target workload are changing so quickly. If you think about like ChatGPT, actually ChatGPT just came out just 1.5 years ago. It looks like it's a long time, but ChatGPT came out, then GPT-4 came out, recently GPT-4o came out, and there will be new GPT-5. There will be no new powerful AI models coming out. So this kind of chip development actually, with just a multi-billion transistor integrated, at least takes a couple of years from initial architecture until the product comes out. You need at least like 3-4 years of development actually. But 3-4 years, like 34 years ago, what was the important model? There was a BERT there, there was a certain model there. But if you target those models, all of a sudden, 3-4 years later, the customer talk to you, I need a much like a larger model to run on your chip actually. So it means that your AI chip, when you design it, it's not only efficient, right? You got to be very efficient. It's the fundamental value proposition of AI chip, but still, it must be quite flexible and programmable enough to accommodate all future changes, right? That makes this problem much difficult problem actually. Rather than optimizing your chip for just one purpose, but it's still difficult, but it's kind of makes your job simpler and more focused. But imagine that you are designing some city or you are designing some building, and the purpose of this building, how people use this city or this building or city, are gonna be very open question, let's say. Then your design gets much more complicated, actually. It makes, in terms of computer science, I would say, this makes a lot of our optimization problem as NP hard problem, actually. So it's a kind of, it's actually Greg Brockman from OpenAI mentioning that AI chip needs this kind of breakthrough. So this both achieving this efficiency, also flexibility. Actually, efficiency flexibility is a trade-off relationship. How we achieve both of them is kind of fundamental challenge of AI chips. And our company, we try to solve that problem at the fundamental level while we're building this product. So go to the next stage. Yeah. But I like to first talk about this opportunity again, because a lot of students here, faculties here, I mean, this is a big opportunities in AI, not only computing side, but a lot of application side, because it's gonna fundamentally changing everything. So now a lot of people think, so like every technology is hyperbolic, right? It has some exponential side, and eventually it's a plateau. So we'll say the initial kind of AI kind of development is in some sense has exponential kind of progress and plateauing at a certain level. But if you look at more enterprise or on your kind of our daily life perspective, the AI is actually just starting at the moment. Probably you see the announcement yesterday from Apple, like they are integrating all this kind of ChatGPT stuff into your personal computer, meaning that, signaling that AI is really getting into our main daily lives right now. It's not only our personal lives, but if you look at all the enterprise are seriously testing right now. It's not big adoption yet, but they are testing all those ideas and they are aggressively pursuing how to apply AI to their internal productivity or their own service product, actually. So, because we are based in Korea, so we are also talking to many enterprises there, such as LG or Samsung, all those companies. They are seriously actually applying AI to their internal development. Let's say all those all the factories, all those chemical kind of synthesis problem, battery problems. They are seriously applying AI to all those their own product development, and we think that it's really right now happening here. So I think it's going to be great opportunity for all of us to utilize AI to solve new problems, to create kind of new service and products. So in summary, we have kind of so key challenges of this new generation of AI chip. I mentioned it should be very efficient, but also it must be very programmable and scalable. And also, like a third important thing is it must be easy to deploy to your new applications. So achieving these three goals are a very difficult thing to do, it turns out. But we try to bring out the product that can meet all these conditions. Once we meet all these conditions, we think we can make a big transition from GPU-based computing to this new paradigm of more efficient AI computing. It hasn't yet occurred, but like there is, we are like making a big transition from gasoline car to electric car. We believe that once this product gets more matured, technology gets matured in right direction, we can make a big transition to this more efficient computing solutions. So next slide. We actually publicized our architecture, our foundational architecture to ISCA. If you know about the ISCA, ISCA is the premier computer architecture conference, that introduced many novel computer architecture kind of concepts. Our architecture is published this year. So you can look up the internet and you can just read all the details of the architectural details of this our chip. We call our chip architecture actually tensor construction processor because we think tensor construction is a fundamental primitive operations for all this AI computing. So if you read one of the papers reviewer, they kind of commented that our tensor construction processor is hits a good sweet spot of being generalized for many tensor-based networks, but at the same time, specialized enough to exploit many of the commonly known tricks of structural parallelism in acceleration, meaning that they recognized our kind of effort of building the solution that are both very efficient, but at the same time, generalized enough so that it's a future to host the coming DNN architecture. So it captures a very good, it well captures what we try to build with our solutions. So next slide. Well, it continues another reviewer's comment. All these decisions are well motivated. So I encourage you to take a look at our paper you are interested. It's a kind of 10-page paper. I encourage you to take a look. So next slide. We mentioned that we already have our first gen product called the Warboy. Our second gen chip definitely are focusing on this transformer-based LLM, small LLM, or all these transformer-based powerful AI models. But our first gen architecture actually more focused on computer vision, primarily based on the CNN convolutional neural nets. But still, the fundamental architecture and ideas remains the same, actually. So with our first gen product, we demonstrated it's kind of performing much better compared to the corresponding GPU product in terms of its performance and energy efficiency. So our first gen product really kind of proved it. It's not only paper, it's proved it with a real silicon result. Next slide. So getting back to our second gen chip, so if you look at also the hardware spec of our second gen chip compared to NVIDIA's, let's say, highest end GPU solution, it not only has the higher memory capacity, which is really important thing because you need to hold the entire memory into your fast memory as much as you can. Also, so we have quite kind of good memory performance even compared to NVIDIA's highest end solution. But you see the power, noticeable thing is power here. We consume way less power than NVIDIA. So meaning that your performance per power wise, we are trying to achieve at least like 2-3 times better than the current solution. So if you say you're spending like 100 watt, you're spending like almost 30-40 watt, meaning that you save tons of energy cost. You're saving energy cost is not only electricity. Actually, if you consume more power, meaning that you're generating more heat, meaning that you cannot put densely, you cannot install your computing densely into the given space, meaning that you need to have a very big data center real estate space. And also you need also a lot of power to cool down this chip as well. So your also a lot of carbon footprint as well. So this energy efficiency is very fundamental, also cost savings as well. So next slide. So yeah, so we try to achieve the 3-4 times better energy efficiency. We'll show not only we are having the high performance, but like we'll try to achieve very good like energy efficiency. As I showed, we have this silicon right now internal testing. So we'll plan to demonstrate the real silicon benchmark result around August, pretty soon after, around like 2 months later. Next slide. Another very important equation for AI chip is your software development environment, actually. It turns out it's also this your software kind of a development, your programmability is kind of fundamental bottleneck to the adoption of AI chips. Because as you know, the GPU, especially NVIDIA, provides CUDA API, right? So CUDA is a kind of low-level API where you can program NVIDIA GPU with a quite high performance, actually. So unless you can provide very good programmable API interface, no matter how good your architecture is, it's very hard for software developer to use your chips. So from the beginning, your architecture, your hardware must provide well-defined programming models to your upper-level software stack. So when I talk about upper-level software stack, on CPU side, it's more like OS and the compiler. But AI chip also has a corresponding software stack called like AI chip compiler. So the purpose of this AI chip compiler is that given the neural network that is described in more abstract form in, let's say, PyTorch or TensorFlow, kind of high-level description of AI models, then your compiler needs to lower and translate that high-level description of AI model map it into your silicon computing unit as much as possible. That's why we call this automatic kind of a translation lowering of AI model into your silicon. We call that software as AI compiler, actually. It turns out, I mentioned about it, a lot of those optimization problems are actually NP hard, very tricky mathematical problem, actually. It's why AI chip development is not easy thing to do. So you got to have your silicon at the bottom, but on top of it, you got to have very solid compiler stack. And on top of it, you got to implement, you got to kind of connect your all the deep learning frameworks at the high level. I think that a lot of students and faculties are probably using those PyTorch, sometimes CUDA low level, but we need to provide those kinds of good programming API so the developer can use and hack and test what they like to do. So it's what also our company is working. Out of like 100 engineers in my company, 70% are software engineer actually. Only 30% are hardware side, but 70% are software engineer developing those software stack that can support the developer and the developers and all this developer ecosystem. So next slide. And ultimately, the entire solution must be easy to deploy under any kind of cloud software stack and the cloud hardware infrastructure. So we also provide a lot of good tools, such as a profiler, debuggers, and Kubernetes plugins, all those kind of software kind of modules as well. That makes it easy for our developer develop their software, but also deploy them easily on their environment, actually. Yes, so it's a kind of, the last part. I just like to mention, as a startup company, it's not only idea, the important thing is execution and also productization and the commercialization. That's also not especially challenging part, especially someone who aspire to do a startup company. I mean, you need to build a product, right? That ultimately you need to build a really good product. And on like a semiconductor startup like us, that's a very challenging part. But it turns out if you meticulously schedule and execute, then a lot of people actually, when you started, kind of told us it's impossible. Don't do it, actually. It's a big company's task. I mean, it's only Samsung or NVIDIA or Intel's job to build this kind of a chip. I also, from the big company, before starting this company, I worked for Samsung, I worked for AMD. So I knew how not easy it is to develop semiconductor product because it involves so large team and a lot of capitals. But it turns out, actually, it's doable, actually. But you got to do it in much kind of smarter way. And in some sense, you got to do it much more automatic way. So that like a small number of people can execute a kind of a large scale project. I mentioned about this transistor has 40 billion, actually. Meaning that a lot of this chip building process must be kind of a design process, even design process must be quite automated. And we also believe in the potential of each individual member. It's usually a big company is kind of bureaucratic, right? So they assign very specific role to you. It's no matter what, because it becomes big. But as a small company, we expect you to play a huge role, a much more like a larger role, and we realize a lot of people live up to that expectations from my experience. So next thing. But yeah, I mean, just previous slide. So you see that, previous slide again. Yeah. So, it's like our design usually is sent to TSMC, and they make, based on design, they make the photo mask, and photo mask goes through this so-called like EUV machine, very like sophisticated photo lithography machine to build this chip, actually. So it's amazing to see. I'm also amazed by all this technology that enables this kind of sophisticated devices, actually. So next slide. So next slide. Yeah. So previous one actually showed that our first chip is already commercially deployed in some of domestic data centers. And we are launching our second gen chip later this year. So we are expecting quite good kind of momentum and adoption of our second gen chip, because this chip is targeting large language models. A lot of enterprise and people are using this large language model. So we see quite good exploding demand for this computing solution, especially efficient and energy efficient and cost-effective solution. So we are launching this product pretty soon. So hopefully at the university level, we like to engage with some students and faculties to develop some good solution together as well. We can sample this chip. I think we can later this year. The next one. This is our roadmap. So we are having Renegade right now, but we have another product coming up as well, like Renegade S, which is a more scaled down version. Renegade Turbo, which is very upscale version as well. We are rolling out new product, next one, based on the same Renegade architecture. So next one. Yeah. Yeah, it's all about the team, actually, I said. It's like we are a startup company, so we don't compete with our capital. We don't compete with our connection, right? I mean, we are all competing with our passion and energy and our focus, actually. So I mentioned that we are about 140 people team, like mostly 85% engineering. And we also publicize some of our works as well. I just like to emphasize it's a really good time, the kind of our team effort to achieve this goal. Yeah, next. Okay, so it's Renegade's upcoming, and we are very excited about this product launch right now. Okay, yeah, this is pretty much it. And if you have any questions, just feel free to ask. Yeah, go ahead.
The strong benefits of your chip is a general purpose chip, right?
So we're not considering us as a general purpose chip, but we are more focusing on kind of a domain specific chip for AI. So it's a kind of a different direction. So domain specific chip for AI, but general enough to run a very diverse spectrum of AI models. Yes.
But it's effective with small language model and large language model.
Mm-hmm, mm-hmm. Yes, yes, yes. Yeah, we can run both of them, actually.
Okay.
Yes.
I think it's your invention is so good to deal with scaling hypothesis when you get more data and more complex model, and it takes a lot of energy to run the model.
True. True. Yeah.
So
yeah.
good.
Yeah, I agree. I agree. Yes.
As a student, I would like to know what is hardware library, such as NVIDIA side, they use CUDA, and what is your hardware library? We have to learn.
Sure. Yeah, that's a very critical question, actually. So I mentioned, definitely we have a quite different level of API. So at the lowest level, actually, I can teach you, actually, if you join my company, I can teach you. It's like what our compiler team is doing right now. Our compiler team, very bright software people, many of them just out of the college, usually getting their master or sometimes PhD, sometimes even bachelor. We teach them at least 1 year how to program our chip. So it's not easy. That's very low level API. So you got to know in and out of what's going on with the hardware. But at the highest level, we are providing PyTorch API. So if you program PyTorch, you can just run it. So in between, like a very low level, high level, there's kind of middle language, such as CUDA. We are right now thinking of supporting Triton. Have you heard of a Triton? You know it's a Triton?
No.
Yeah. Triton, it's an open source model. It's developed by OpenAI, actually. And the Triton is almost plays the same kind of a role as CUDA, but easier than CUDA, actually. So our plan is that we'll provide those Triton API or the equivalent API probably next year. So that's our plan. Yeah.
Okay. Can we imply we just know only PyTorch for system integration, right?
So the question again?
Can we imply we just only know for PyTorch library for implement AI in for industry, right?
Right, right,
Okay.
right.
Oh,
yeah.
I have a few questions. Okay. Your chip performance is so good. As a small entrepreneur, is there any personal computer GPU for a student like RTX something, not a enterprise chip?
Oh, okay. Yeah, you can definitely install. You can have. We can provide you with the desktop version, so that you can play with actually. Yeah, I'll talk with some faculties here how we can provide those computing to students here, like for free. So you can play around it actually. So if you let, but you got to make sure you got to use that. You got to play with it actually. Yeah, but yeah, you can use it in the desktop environment. Yeah.
Okay, that is so good.
Yeah.
Thank you for your
Okay.
answer.
Okay. Thank you.
ขอบคุณค่ะเอามีคำถาม
Hello.
Okay.
Okay, so I have a question about the intercommunication because NVIDIA have something like NVLink that can allow you to like communicate between the GPU and or even the multi-node. I would like to ask that if your chips have some kind of this feature that allow your chip to be able to communicate for a larger scale of model.
Sure.
Okay.
Sure. Yeah, that's also a very good question. So to run like very large language model, you need multiple chips to run them. So we provide chip to chip, but we don't have a kind of dedicated chip to chip such as NVLink, but we are just using PCIe kind of link for a chip to chip purpose. But I'll say it's inference. The chip to chip bandwidth required for inferencing is way lower than chip to chip for training. So for training, for example, you need to synchronize all these weight parameters, right, to all of the chips actually, meaning that you need like really a lot of bandwidth because you need to synchronize, broadcast all these weights to update the parameters of all these in different chips actually. But inference, if you think about it, you are just transferring all the intermediate results from one chip to next, actually. So the bandwidth required for inference is way smaller than training. It's why we think PCIe Gen 5 bandwidth will be good enough. So in the first answer is yes, we provide chip to chip, but we are using PCIe for our chip to chip at the moment. But for our next kind of roadmap, like the chip we are planned to roll out the end of this year, we also plan to implement dedicated chip-to-chip, not as a high performance as NVLink, but sufficient enough to run very big models. So yeah, so that's our plan and our current providing actually.
Yeah. Thanks for your answer, but I have one more question. I saw on your slide that you have the RNGD server that have like 960 gigabyte of memory. Do you have any like a picture or some of that server? I want to know like what kind of server.
Oh yeah, we have some server pictures right now currently testing at the moment, but I think let me check. I can show. So it's in our internal Slack. But I can say you this actually. This chip, you see this one. I mean, let me show you. Yeah, because you asked about the memory. Yeah. So you see the chip, right? And this one is a memory, actually. This is the one stack of HBM3 memory. So each one is 24 gigabyte, actually. And another one is 24 gigabyte. So these two HBM3 provides a total 48 gigabyte of memory. So in one Fourier server, we install 16 or 20 of this one. That will provide equivalent like a 960 gigabyte of memory. So it's just, you can say, it's just like 40 of this memory stack inside the server that provides the capacity, actually.
So it's just like a normal server with a, is it like on a server rack or like a tower?
Yeah, it's just a regular server. It's usually like a Fourier server, like from Supermicro, let's say like ASUS, or all these HP and Dell. It's very regular server. So we are providing the same form factor as NVIDIA GPU PCI card, actually. Yeah, yeah.
Okay,
So,
thanks.
Yeah. Mm-hmm. Oh, yes, yes, we can do it. We can do it. Yes, yes, exactly, exactly. It's what we are planning. Yeah.
Any questions? Okay.
Okay, for the hardware, so what is the bottleneck of the AI chip right now? So it's like a memory bandwidth or like heat dissipation?
So your question is, what's the...
what is the bottleneck of the AI chip right now?
That's also a very important question. Yeah, it's definitely the memory kind of a performance becomes more and more bottleneck because this large language model, you need to provide all this data from memory to your chip. So it's definitely getting the bottleneck right now. And also energy becomes another bottleneck. If you see all the NVIDIA's product roadmap, I mean, their chip power consumption, right now I think Blackwell is almost like 1500 or watt or something. So you need really liquid cooling and a very new, different like kind of data center design to power all those chips. So energy, definitely, energy and memory are one of the fundamental bottleneck right now to AI chip, actually. Yeah.
Okay.
What is your vision for the future of AI acceleration, and how do you see Furiosa AI's technology shaping that future?
Thank you. So what the first question is, what is that, AI distillation? So,
Yes, about your vision of AI acceleration.
oh, it's a future of AI acceleration. Yeah, it's you need a much more acceleration, right? So acceleration is about efficiency, right? It's not very general purpose, but sufficiently general purpose, but it got to be very efficiently accelerate. This is more focusing on the target workload. So we are expecting right now every server in the future will have AI accelerations, we believe. Most of AI, at least like 50% of all the servers. And we are talking about also notebook and desktop. We are talking about right now AI PC or AI smartphone, right? So every kind of major computing platform will have more and more of acceleration. Right now, the most important acceleration target is AI, but we'll see. It can be AI, but there can be other workload as well that needs more acceleration. So for your questions, we'll need much more acceleration because the other thing is like people are talking about Moore's law is dead and all those things, right? I mean, So only way we can achieve more efficiency is we do more domain-specific approach, which accelerate a target workload, actually. Yeah.
Thank you.
Okay. So, okay. Yeah.
Okay, thank you. At a small entrepreneur and the top company, we are looking for alternative from NVIDIA. And your performance is interested. We are looking for reliability from the alternative chip company. Can you provide us for success case from Warboy and Renegade from you? Can you provide us?
So your question is more kind of availability of those chip or more kind of reliability of this chip? Both of them, or?
Reliability from the success case that we have to reference from the success company use your product, and we convince our customer to use your product.
Oh,
for
I see your point. Yeah, I mentioned our first gen products are already deployed in some of our data centers in Korea. But with our second gen chip right now, one of the major our partner are quite good sized enterprise company. I mentioned the LG, Samsung, Naver, and Kakao. They are all like about to test our chip. So there will be good reference for another customer actually. So we expect some of our solution will be already deployed by the end of this year. So yeah.
Okay.
My last question probably.
Okay, my question.
Okay, yeah. That will be my last question today. Yeah.
Okay. What do you think about your competitor like NVIDIA or chip company in China? Because last year they developed it so fast.
Yeah. It's a very competitive area because it's a very big market and big opportunity. So a lot of big companies, not only just like startup like us, but also big companies are all jumping into these opportunities. So it's a highly competitive area. But one thing I can say is I think a startup has advantage here. One of the reasons is that it's just changing so fast. So you got to move very quick. So it's why OpenAI is better than Google these days, right?
Yeah.
So I think the startup has definitely advantage in this fast changing environment. And regarding the NVIDIA is very dominant right now. It's the king of the king these days, right? I mean, if you look at the market, it's for the right reason. I think they have the good product, actually. I'm not saying NVIDIA product is bad, but I just mentioned that it has a fundamental limitation in the efficiency area, actually. So as long as we can provide a compelling hardware, also software stack, I think it's not like we're gonna entirely replace all the GPU there, but we'll have our own segments and our own good market. And eventually we think we can make a more transition from kind of GPU to this chip. Yeah.
Okay, thank you.
Thank you. Right.
Okay.
I'm so curious with your result. You see, the last line is fixed point 8-bit. This from this table. You see, it seems like your chip is lower performance than NVIDIA, almost 60%. I'm not sure what is the benchmark for this. Your evaluation benchmark.
Sure. So probably the next slide. Next slide. So this is the benchmark right now.
Llama 7.
Llama
billion
7B
parameter. Okay.
parameters.
Okay. Can you next to slide number 3? Next. You see, usually for NVIDIA, the weight is double, 32-bit. But in comparison, I'm not sure that your chip can run over for 16-bit fixed point or not.
Okay.
But you see, you have more steps than quantization, calibration. This is usually way for your chip to deploy the model into the card?
Okay. Okay.
Thank
Yeah.
you,
Okay.
thank
Good
you.
questions. And the first question, actually, we just have our first benchmark, which is based on simulation, to show you. But we release our real silicon benchmark for Llama 70B, not 7B, the largest Llama model, in August right now. So we are preparing for new release of benchmark, because this silicon just came out a month ago, actually. We are right now trying to obtain all the benchmark results at the moment. So we can share our Llama 70B benchmark results with you in August. So so that's my first answer to your question. So we can run very large models as well. So your second question is about quantization tool, right? So every chip company these days provide a quantization tool, right? I mean, so that like you can quantize kind of big models. Quantization means it's not like you are reducing your parameter count. You're just changing your numeric type from FP16 to integer 8, or even like integer 4, FP8. Then like you can reduce the storage amount by half or 1/4 actually. So yeah, we are providing quite good quantization tool, but NVIDIA is also providing the same thing actually, I would say. That answers your questions, or? Okay, okay.
Okay,
Right.
from my question.
Okay.
To my understanding, the chipset could store multiple models that have been trained before. Then the chipset would run interference to obtain prediction results, or classification depends on use cases specific. And I have two questions. How many models that can be stored in the chipset? And the second one is it possible to consider model generalization such that one model could be generalized enough to train different data sets from different condition scenarios?
Okay. So the first question was how big models we can support with this chipset, actually.
Yes.
So I said this single chip has 48 gigabytes of memory, actually, meaning that this single chip can support the model size roughly around 20B or 30B if you do quantization, the integer A quantization. But if the server chipset will have almost 30 of this chip inside, meaning that you can 30 times 20B, meaning that like it can support up to almost like a 500 billion parameter size as well. So we can support small model, but if you on the server level, you can run almost like a couple hundred billion models as well. That's my answer. So, and what was your second question again?
And the second question, is it possible to consider model generalization such that one model could be generalized enough to train different data sets from different condition and scenario?
Yeah, definitely. It's what this big model is all about, right? So small model is more specialized, but big model is much more generalized capability, actually. So I think, yeah, so the big model can do many tasks very well, but you got to pay the cost. Actually, it's you got to pay all the computing cost for that, actually, yeah.
Okay,
Yeah.
and the last question, what are the most challenging problems when applying supervised learning or deep learning reinforcement method in the chipset?
Oh, okay. That's also so from the chipset point of view, I think the supervised learning, unsupervised learning don't make that difference for us because the underlying model architecture is pretty much the same, actually. But reinforcement learning can be a little different because because it needs, it has some component you need more CPU there. But most of the chip vendors are these days care about transformer models, and they don't care much about reinforcement learning. It's like actually reinforcement learning actually are based on also transformer models. So I'll say the chipset companies care more about the concept of those transformer models actually at the moment. Yeah.
Thank you so much.
Okay, thank you. But they care about the MOE these days. You know, the mixture of export is kind of different computing patterns actually. So from chipset point of view, we care about like, what's the sparsity there? I mean, the MOE, like a mixture of export, is like a coarse-grained sparsity or more like a fine-grained sparsity. That's very important actually. So we care more about those kind of things actually as a chipset company. Yeah.
Thank you so much.
Right.
Any questions?
I'd like to ask about your a bit more in detail about your architecture. You said the TCP architecture was kind of generalized, right? So I'm guessing not only will it do like inference, which requires like small bit widths and data structures, as well as like training. So does your chip do like accelerated 64-bit multiplier accumulate, or just down to 32 FP32 FP16?
Oh, okay, that's a great question actually. Yeah, we support the training basically. So we don't support FP32. So our highest level numeric format is BF16. But internally, we have a 32 kind of units, 32-bit units, because even though 16-bit units you accumulate, you need the 32-bit units. So, and also difference between inference and the training from computation point of view, is pretty much the same, right? Inference is just forward the computation, but training is forward and backward. But so training definitely needs more kind of general, because you need to accommodate all the experiment from all this. So inference you can be a little bit more focused, but computing point of view, training and inference at a single chip level is pretty much, I think, will be the same. But the difference is training is not only single chip these days, right? It needs almost like cluster level. Usually you need like 10,000 chips kind of working together to train one models. But inference, if you think about that, inference is different. Inference is just for processing one request at a time, and you don't do inference with a 10,000 GPU, actually. Just probably single server or single chip, or like a little multi-node will be the economic kind of unit to service inference. So there are definitely differences between training system and inference system, but at the single chip level, I'm saying is system level is quite different, but single chip level, they have a lot of commons actually. Yeah, that's my answer. Yeah.
So given your architecture, will support only accelerate BF16 and maybe FP16. So
and also FP8, integer 8, and the integer 4. We are supporting integer 4. Yes.
4 too.
Yeah.
So I would probably guess that your training would be kind of limited by a couple of factors, like the bigger like size weights, like FP32, and as you were saying, you don't really have a chip-to-chip interconnect yet, right?
Oh, we have one, but it's not dedicated actually.
Oh, okay.
Yeah, we have a PCIe chip-to-chip, but like compared to NVLink, it's like 1/8 the performance. So it's kind of slower than NVIDIA. Yeah.
As you were saying, you needed to like kind of like somehow like collaborate them all together, all the different chips, right? And PCIe 5.0 X16 lanes is 128 gigabyte per second,
exactly.
right?
Exactly. Yeah.
So there's a limitation if you use extremely large language model. You train them, right? So you probably are limited to medium size, or the lower part of large size, right?
Yeah. That's so true. And it's why we say we are more focusing on inference rather than training. definitely we can do, I think, some fine-tuning training. Fine-tune training is not like, it's a kind of way smaller scale than pre-training, right? So we expect that our chip is capable of a fine-tuning level. But as you said, like this lag of NVLink and the relatively smaller kind of performance, and kind of a little smaller performance compared to NVIDIA's highest end, kind of limits our usage in the training, right?
As engineers, we're probably very interested in very low-level functionality. So if I may ask, the Renegade ISA or even the IR representation, do they have like permute instructions or like anything that is somewhat like overlapping with FPGAs?
I doubt, but yeah, those permute, we can kind of generalize it as a kind of reshape, actually, reshape functionality. So a lot of data layout, we need to permute, not only permute, but like we need to do a lot of kind of data shuffling and all this data kind of reshape. That's very also difficult part of AI chip development, actually. So it's in combination. So there are some hardware functions that automatically, you just ask them to do it, they will do it, hardware do it. But there is also a compiler part, software part that needs to take that job. So it's kind of combination of hardware. So we always are thinking about, okay, we'll put this function more into hardware, or we'll make this software compiler will take care of this one. We always make that kind of decision about those kind of permute and data reshape area, actually. And for technical detail, I mean, if you type like RNGD tensor construction processor, our paper is already publicly available. So you can just read. It doesn't contain every detail. So please if you have any questions, just let me know. I'll share my email. But yeah, so that's a great question, actually. Yeah, my answer is that it's both the co-design of the software and hardware, actually. Yeah.
So are you going to move into like different segments too? Like you were talking about like, the proliferation of like AI PCs, AI phones and all that. So will you be moving to kind of like push into the same region as like Google and their Pixel or their Coral like processors?
Yeah, that's also very important question about our roadmap. What are you gonna do about those devices, actually? Because we are right now focusing on kind of server side. This product is focusing on server side. On device side, we think, so kind of if you develop AI chip for mobile side, those chips must be very low power. I mean, it's like 1 watt to 2 watt scale. This chip is like 200 watt or 150 watt. So it's a very different kind of design, actually. So it's gonna be hard for us to move into those mobile area. But the next area we can go into is AI PC. So PC desktop or PC laptop. Probably we can scale down our solution to get into those areas. So, but that's our important kind of roadmap decision as well, whether we're gonna go there or not, actually.
If that's your roadmap, may I provide you with my wish list?
Okay, sure.
Would you somehow connect it with RISC-V and make it a unified memory model such that we can train huge memory models on that processor without having to pay too much?
Okay. Sure. I'll take it. Okay. Thanks
you.
for the advice. Yeah. Hope we can continue discussion more about it.
Yes,
of course. All right.
ขอบคุณค่ะ Any questions? Okay. And now I want to say thank you so much for a very great speech today. Please give him a big hand.
ภารกิจของเราคือการสร้างชิป AI ที่สามารถรันโมเดลที่ทันสมัยที่สุดในโลกได้อย่างมีประสิทธิภาพมากที่สุดเราเชื่อว่านี่เป็นส่วนสำคัญในการทำให้การประมวลผล AI มีความยั่งยืนตัวแทนจำหน่ายอย่างเป็นทางการในประเทศไทย FuriosaAI Card Wallboy สำหรับ High Performance Data Center Accelerator for Advanced Computer Vision Deployment on Cloud and Edge และ Renegade สำหรับ The Most Efficient Data Center Accelerator for High Performance and Multimodal Deployment คิดต่อบริษัท iDefense จำกัดโทรหรือ LINE 0817355992